Hi, so stimulus responsive polymers are important in terms of their interactions with microbes. We've been looking at how we can use polymers that respond by a desolvation transition to manipulate bacteria, both in terms of diagnostics and as tools for discovery and monitoring the environment or clinical situations. Now, really briefly, we take branched water-soluble polymer with specific ligands attached to the chain ends. These polymers bind to specific targets on our microbes. When they bind, importantly, they go through a desolvation. So segments, and you look at the black bits of my cartoon here, lose water, desolvate in a process that is really very similar to protein refolding. Now, the important aspects of this work is that when the polymer goes through this transition from this open, swollen, solvated state to this desolvated, what we call a globule, its physical properties change and its cell adhesiveness changes. And so that allows us to form aggregates of bacteria, or in fact other microbes such as fungi, in a selective manner. And here you can see a polymer that's targeted to gram-negative species. We form what we call these mats, which are essentially aggregates of polymer and bacteria at 37 degrees. And then cooling them allows us to disrupt the mat and release the bacteria. Here you see another image, this time as an optical micrograph, where we can see the polymer dyed blue, the bacteria dyed red. 37 degrees, we form these aggregate complexes, and then we cool the system to 4 to release the bacteria. Here, this is another polymer. This time it's a gram-positive selective polymer, and in the electron microscope you can see the Staphylococcus aureus in the absence of the polymer, and then aggregated after we've added that selective material. These are being used by us as diagnostic devices for selectively detection of pathogens, but also as sampling systems. And clearly we can take these aggregates and use them to manipulate the bacteria. An aspect that is very current for us now is to add the polymers to immobilized scaffolds, and in this case we've added the polymer to a polyurethane foam, and you can see the white bits here that are space within the foam, and the red bits are the polyurethane. Now, this is a polyurethane foam in the absence of bacteria. You can see that there's no bacteria present, and here we've added Staphylococcus aureus, so you can see all the bacteria here as these black flecks. Now, this is important in a number of ways in terms for discovery. First of all, we're extremely interested in talking to anybody with ligands, right? So there might be ligands that have been discovered with the idea of making an antibiotic, but actually not effective as a therapeutic. We're certainly interested in anything that binds selectively to microbes. But also these are tools for discovery as well. And for example, we're using the polyurethane system, beginning to use it in the environment, in the riverine environment, to sample the bacterial load of rivers. Okay, so thanks for listening. If you want to speak to me, do email me, stoprimmer@bradford.ac.uk.